Until now, we have decomposed things according to well-established and pre-specified abstractions, like perception, state estimation, control, and planning. We have also talked a few modules ago about deep learning and convolutional neural networks. Another option is to replace all of the previous abstractions that we discussed with one model that is learned end-to-end. In this module, we will talk specifically about the reinforcement learning paradigm. The key formalism that we will use to discuss and analyze these approaches is the Markov decision process, or MDP. We have seen in previous modules the idea of Markovian state. To review, this means that the state completely characterizes the underlying system. In other words, the future is independent of the past, given the present. The MDP is defined on a state that follows the Markov assumption and has the following components. X is the state space, U is the set of actions or possible inputs, T is the probabilistic transition model, R is a reward function, and gamma is a discount factor. Some of these things, like the state space, the transition model, and the actions, we have seen before, but a few of them are new. The reward function tells us, given we are in a state X and we take an action U, how good is that state-action pair? Let's consider a toy example of our duckybot in the lane. Perhaps we define our reward as the distance the duckybot travels down the lane. If we're in the center of the lane, pointing down the lane, then we will get high reward by driving straight. One thing to keep in mind here with respect to autonomous vehicles is the question of where is this reward coming from? In order to compute the reward, we need to know the state, and as we've seen, this is not something that we have direct access to in general. We might not just care about the immediate reward though, since maximizing this might be very greedy and might not lead us to good plans in the end. As a result, we can define another variable g, which is the discounted sum of the rewards from now until the end of the time we care about, assuming we took some sequence of actions and visited some sequence of states. This is where the discount factor gamma comes in. Gamma has a value between 0 and 1 and controls how much preference we want to give to rewards that are obtained sooner. For example, if our duckybot is pointing at an angle, it might yield a higher return to turn first and then go straight, even if going straight right away might have yielded more immediate reward than turning. Also note that we are omitting the observations here. In the case that the state is considered to be partially observable, i.e. the state is observed through sensors, then we can extend this formalism to the partially observable Markov decision process, or POMDP. A POMDP is defined by all the things that define an MDP, plus a space of observations, Z, and the measurement model, O. In our end-to-end framework, we can also consider the camera pixels to be the states, and then they become directly observable. In the nomenclature of MDPs, what we are looking for to control the robot agent is called a policy. The policy tells us which action to take given the state we are currently in. In a deterministic policy, we will always take the same action when we are in a certain state. In a stochastic policy, there will be some probability of taking different actions. In this module, we will discuss approaches to find this policy iteratively by letting the agent act in the world and receive the rewards for its actions, a procedure referred to as reinforcement learning. The MDP framework is extremely general and can apply to almost any robotics planning problem, including ones that we have already seen in the planning module.